paper is based on a white paper that was written by Subodh Kulkarni, who's our CEO, Sean Langbridge, who's our European sales manager, and Richard Johnson, who's our director of engineering in Singapore. So if you want more information, this goes at a high level. You want more information, it's on that white paper, which can be found on our website. So today I'm going to cover 3 topics, all relating to smarter inspection. Solder paste inspection, which covers true volume measurement. Print process optimization, using accurate SPI data more efficiently, and SPI has been already defined here by Runsheng as solder paste inspection. And then lastly, going into AOI, discussing changeover and false call optimization by using advanced modeling techniques in AOI. So before I kind of go into what smarter inspection is, let me just define what I mean really between inspection and smart inspection. Inspection is pass and fail. Defect, reject, rework, good, bad. That's easy. Anybody can do that. That's kind of your basic inspection. When I talk about smart inspection, what I mean is something that prevents defects before they happen. And not only prevents it, but improves your process and gives actionable results to improve it before any kind of defects happen. Ultimately, all that goes down to reducing cost. So, in SPI, why is SPI important? How do you get accurate SPI? And then once you get accurate SPI, what do you do with that data? I think everyone knows that solder paste printing actually encompasses more than half of all SMT defects. It's just a fact of it. You've got bridges, you've got shorts, you've got registration errors, BGA issues, all kinds of defects come from the solder paste printing process. So therefore, SPI is important, especially with all the smaller components that you're getting down to the micro BGAs. Accurate data enables informed decision making and gives you direct correlation to make accurate results. Sensor and measurement algorithms play a significant role in getting those accurate. You can't just take a picture of the image and just, here you go, here's your height data. There's a lot of data that comes in behind getting accurate measurement data out of your solder paste inspection machine. In addition, your measurement of solder paste must be performed repeatably and accurately without calibration drift. You can't have your system drifting off calibration. It has to be repeatable day in, day out, week to week, and line to line. Here's just a couple examples. Up in the top you see basically a traditional solder paste deposit, what it may look like in here. It's got shape, it's got features, it's got high spots, it's got low spots. If you take your accurate data here, what it actually looks like, you can filter that data and it makes it look like a mesa or something. Or you can filter it and make it look like a pyramid based on filtering it to get more repeatable data. The problem is this isn't accurate. If you look at your data here, you might get a high measurement and think you have more solder paste than you actually have, which may cause you to react and change your process when you actually have a good deposit. On the other side, you may think that you have not enough data, not enough solder paste, change your process, and suddenly you've got shorts coming out everywhere. So it's extremely important to make sure that you've got accurate and repeatable data, and it's not filtered. This is just our example of repeatable, accurate, and repeatable. It's important because you've got to trust your data. All the way across the line, machine to machine, day to day, week to week, you've got to trust that data. That's why accuracy and repeatability is important. Even so, that's not enough to improve your process. That's enough to make sure you don't have defects going down the line, but it's not enough to improve your process. That's why we want to talk about smart inspection. Smart inspection is more than just inspection. Smart inspection means using that data from your process and your product to actually predict when a failure might happen. Trend analysis. In fact, smarter inspection goes even beyond that. Smarter inspection means giving you actionable suggestions to improve your process. I give the analogy of you're driving down the street in your car and all of a sudden your engine seizes up. Well, that's a failure. So you could go one step further and say, I've got a gauge that tells me that my oil is getting a little bit low. Well, that might predict that you might be having a failure coming up soon. Well, your car could go one step further and actually tell you, hey, you need to change your oil. Here's the page in the manual to go do that. and here's the steps to follow in order to change your oil. That's what I mean by smarter inspection. It actually goes further down that line rather than just telling you when you have a problem. It's telling you when you might have a problem and what to do to prevent that problem from ever happening. What does that lead to? I think what we're all interested in, reduced cost. So now let's assume that you invested in accurate and repeatable SPI. So you have a machine that you can trust the data, and that's the key part, is you need to be able to trust the data that you get out of your SPI machine. How do you take advantage of that? Well, there's a couple ways. In the preventing and prediction department, you could have closed-loop feedback. You can take your XY registration, feed that back into your solder paste printing machine, and actually adjust for variations that you see. You can use open loop feedback to look at trend analysis and see when something might be drifting, or you've got a clogged stencil or some issues out there that tell you when you might need to take action. It can actually go further on that. Smart SPI can look at, I'll use an example, print direction analysis. So looking at print direction to see what could be happening and give you actual suggestions on what to change your process. Not just that something might be going wrong, but that something that you need to do to change that process. Now that takes into account knowing how the solder paste printing process works. Not just inspecting it, but knowing how solder paste printing works. So here's kind of an example of print direction detection. Your Smart SPI can actually look at it and say, you've got height and volume repeatability errors, so we're going to give you a couple suggestions here. Reduce the separation speed, increase the squeegee pressure, reduce squeegee pressure. It gives you actionable suggestions that your operator can use to improve the process. Here's a real example. This was actually taken at a customer, and I'll show you at the end of this where that went and how that improved the process. So by looking at the print direction, we were able to define that significantly more defects were reported with the reverse direction. Now, most machines could look back and just say, well, every odd print is forward and every even print is backwards, but you can't trust that, because what if the operator pulls something out of the machine and now you've just switched your whole direction? If your inspection machine is looking at it and just assuming that you're alternating print directions, it's not going to be able to handle this. So you need a smart solder paste inspection system that uses that data, and it can know which direction you're printing rather than just assuming the direction. So by using algorithms, it is determining which direction you're printing and giving you actions. As you can see, the trend here before the timeline goes this direction. So you've got your data, it's below your target values, gives you an action to reduce your separation speed. Everything turns green and is with parameters after you've done that. So it's giving you that trend. It gives you actionable results to improve your process. This is real data taken at a customer over a course of 15 to 20 boards of run. That's a significant improvement of 18% first pass yield to 65% on a small number of boards. That's really critical to save money, is you can get results like that extremely quickly. Not only because we're telling you what's wrong, but we're telling you how to fix it before it actually happens. So on the summary of SPI, accurate and repeatable SPI along with improved algorithms can significantly increase your productivity and yields in a short period of time. So I'm going to talk a little bit about AOI now. Traditional AOI systems, I don't think anybody is really a fan of, because they're hard to program, they take a lot of data, they take tuning, they take someone who is spending a lot of time with them, and generally what they turn out being is someone who is passing on the defects, or passing on the passes and pulling out the defects. So you've got a lot of operator intervention. That's traditional AOI, and that's why people don't traditionally like AOI, is because it's labor intensive. What is Smart AOI? Smart AOI is flexible and fast, handles normal component variations, allows easier and faster setup, and reduces the defect review time. That operator sitting there and saying, yep, that looks good, that looks good, that looks good, by limiting or eliminating false calls. That's a lot of words, but how does that actually happen? Well, most AOI systems use traditional rigid algorithms: length, width, color, shape, size, end cap, etc. Each variable must be programmed and tuned. For example, you're looking at a 1208 capacitor. It's a 1.2 millimeter nominal, so you program your algorithm from 1.1 to 1.3 millimeters. Very rigid. You can't go outside those. So now you've got your certain length, and everything has to fall within that. Advanced modeling techniques can help. Principal component analysis is an advanced modeling technique that's used in statistics, facial recognition, and several other things that actually can help, and it's much more flexible, much easier to use, and doesn't require someone with a high PhD in order to program all these algorithms and make sure everything gets tuned. One example of principal component analysis is in facial recognition, as I mentioned. So if you're looking to, in a traditional algorithm, to find someone's face, let's say it's my face that you're trying to recognize, well, you'd look at it, you'd program, here's the color of the hair, the distance between my eyes, the shape of my face, where my ears are, etc. Now, if I turn my head a little bit, or it's later in the day and I've got a 5 o'clock shadow, well, those algorithms probably go out the window because things have now changed. And you'd have to reprogram that. So now you'd say, well, the bottom half could now be a little bit, brown or gray, depending. So you're gonna have to change your algorithms. The problem with that is now you're always tweaking those algorithms. Advanced modeling techniques, PCA, can actually learn where those variations are and adjust in real time to be able to find faces without tweaking all those. So in SMT processes, how does that really work? Well, what it does is it allows fast and simple programming. You don't have to choose an algorithm. You basically choose good and bad. So this component looks good, you add it to the model. The modeling technique. So there's no algorithms. You add it to the model. This component's bad, you add it to the bad model. Now you get another one that comes in, you add it again to the good model or the bad model. The system learns on its own. It's self-teaching. It's a way to handle the process variation. You don't have to look at that width and length and all those variations that could happen. You get a different vendor of your chip capacitor and suddenly the end caps are a little bit larger, a little bit smaller, and you got to go in and reprogram your entire system because now you've got a different component. With statistical modeling, you don't have to do that. It's going to learn. It might say on the first one, well, that's a little bit different. It might tell the user, hey, I got something different here. Is this good? User says it's good, it suddenly learns with one click of the button rather than reprogramming your entire system. Here's an example of all the variations that you might see. These are all good. These could all be good components that you see in there. They've all got good solder joints. All the components are good. They've got variations, color, shape, size, etc. Those are all variations that traditional algorithms don't handle very well. I'll give you an example here. Let's just take a couple attributes. Could be length and width, could be color and shape, etc. You've got a distribution of good, so all these components are good. Now you get a part that comes out here, and this is a bad part. With a traditional algorithm that's rigid, you've defined your box here. You've got your attribute that this is good and this is good for one attribute, and this is good and this is good for the other attribute. Well, it falls within that. So at this point, you'd say good with a traditional algorithm. You'd pass that part out, and you'd have a defect at the end of the line, and your iPhone doesn't work. So what do? Well, okay, let's just move that attribute over. What happens then? As soon as you move that attribute over, because it's a rigid line, you have a bunch of false calls. And now you've got the operator at the end of the line looking at it saying, well, that's good, that's good, that's good. That doesn't help anything. You're losing money because your line is stopped or slowing down because you're passing all these good parts. Statistical modeling can actually look at the distribution of this and fit all these while passing all these parts and rejecting the bad part. It enables zero escapes and extremely low false calls. So, programming. Traditional algorithms, okay, let's just take one aspect. You're programming length of the component. Okay, you've got minimum and you've got maximum length. Your code would be, well, if it's shorter than this or larger than this, okay, then it's a defect. Otherwise, pass it. In advanced modeling techniques, there's really just a probability. So it's going to extract the key variation axis. I'm not going to go into the math behind this or anything because I don't even completely understand it, but it's going to extract the key variation, and it really does is it creates a probability. Does it fall within the distribution of good? If it does, Great, it passes. If it doesn't, it's a defect. Okay, fairly simple. Now let's just take an example of, let's say you've got 2 parameters, length and width. So now you've got 4 things that you're looking at here, minimum, maximum, minimum, maximum. Your code gets a lot longer. And of course, we all know that you've got more than 2. You've got color, you've got variation in end cap, shape, etc. So your code could get really long here as you're doing this. With advanced modeling, the model actually creates its own variation axes, and you've still got your basic code. You tell it where you want that probability line, and you can adjust that, and the code is easy, pass or fail. And it's based on a probability of how close it is to the model. Very simple. This is actual customer data that was taken using a statistical modeling versus a traditional algorithmic AOI system. We see here on the left is after one run, which is 1 panel, 10 panels, and 30 panels, what was the cumulative programming and tuning time? With advanced modeling, you started out with about an hour of time, and it slightly increased with tuning. And again, tuning is extremely simple with advanced modeling because your tuning is, you get a variation, it intervenes with the user and it says, is there a problem with this component? You say, no, that's a good component. It adds it to the model and it learns. Whereas with a traditional algorithm, it took a lot longer to tune because you've got all these steps with algorithms and all the variations that you're trying to program. And every time you've got some kind of switch or some kind of change maybe in the components, your time is increasing exponentially here. False fail is another issue that you have with traditional algorithms. You can see that, yes, it steps down as you go, but you're still talking about, after 30 panels, you're still talking about 3,000-4,000 parts per million. I don't think anybody wants those kind of failure rates, especially if they're false calls. Again, that's the person at the end of the line going, yeah, that's okay, that's okay. Nobody wants to waste time doing that. Virtually 0 false calls with advanced modeling technique after it's been shown enough examples. It learns, and it's a lot easier to program. So, in summary on AOI, it is possible to get smart AOI. It is possible to have AOI that's flexible, fast. It handles that variation that you're going to see from reel to reel, component to component, board to board. It allows for easy setup, and it reduces that defect review time of that guy sitting at the end of the line and punching the button. Smarter inspection is what you should be asking for from your inspection companies, and what that really means is not just finding defects, but predicting when defects might happen, and then telling you what to do to eliminate and avoid those defects before they happen, not just telling you when they've happened. That's my summary. Demand smart inspection for your SPI and AOI systems.